Okay, so we're not going to go over 12.4. You won't see that anywhere on the test. So let's just skip to 12.5 and making predictions. All right, so last time what we looked at is we tried to find the numbers for A and B for our linear regression line. Now what we're going to do is we're going to make predictions using this equation. Remember, this was the equation used to make this line right here, where you had your data points out here somewhere. Okay, so this equation is for this line. This line is an estimate for all your actual data values. Okay, so if we know the slope and the y-intercept, or if we know A and B of your regression line, then we can plug in any value for x, and we can predict the average. Okay, that's important right there. The average value for y. So it won't be an exact value because we're using this line to make predictions, and this line is an estimate to these data points right here. Okay, and just FYI, if your data doesn't resemble a line to begin with, you shouldn't use a line to fit the data and make predictions. Okay? Alright, so when we're doing correlations, it does not matter which variable you choose for x and which one you choose for y, as long as you're consistent with all your choices. Like all your x values will go here, all your y values will go there. But when we're making predictions, the choice of x and y does make a difference. Okay? So how you choose what is x and what is y is right here. Y is a variable that you want to predict. X is a variable that you're using to make that prediction. Okay, that's it. So for example, say you're using the number of times a population of crickets chirp to predict the temperature. In this case, you would make the variable y the temperature, because what you're doing, you are predicting the temperature. Y is a variable that you want to predict. X is a variable you're using to make that prediction. Here, what are we using to make the prediction about temperature? Well, the number of times a population of crickets chirp. Okay, and the x variable will be the number of chirps. Okay, so y can be predicted by x using the equation of a line, that y equals a plus bx, if a strong enough linear relationship exists. Okay, well, how strong? I'll show you here. Okay. Also, what you can call your x variable, that can also be called the x variable or the explanatory variable. Okay, because if x changes, the slope tells you or explains how much y is expected to change in response. Your y variable, and by the way, this can be x variable, this can be the explanatory variable, it can also be called the independent variable. Okay, your y variable is also called your response variable, and it is also called the dependent variable. Okay. In the case of two numerical variables, your x and your y, you can come up with a line that enables you to predict y from x if, and only if, the following two conditions are met. Number one, the scatter plot has got to look like a line. Okay. Number two, your correlation R is moderate to strong, or typically beyond 0.5 or negative 0.5. So remember, R can go between -1 and 1. So if we have a number line here, here's 0, here's +1, here's -1. Then what they're saying is from 0.5 and -0.5, so if this is 0.5 and this is -0.5, from here onward, or from here onward, if your R goes from -0.5 up to -1, or if your R goes from 0.5 up to 1, that is moderate to strong. And then if you have an R that is moderate to strong, as well as a scatter plot that looks like a linear pattern, then you can make predictions. Okay, this is just FYI. Some researchers don't actually check these two conditions before making predictions. Therefore, their claims are not valid. Okay, because these two conditions have to be met in order for you to make predictions. Okay, but suppose your correlation is high. Do you still need to look at the scatter plot? Absolutely. In some situations, the data will have a somewhat curved shape, yet the correlation is still strong. Okay, so your R will be moderate to high, but you won't have a linear relationship. You always need to check both of them before you move on to predictions. Okay. All right, now say we want to find out how much water in ounces a person will consume if the temperature outside is 95 degrees Fahrenheit. So here's our regression equation. Okay, so first off, I need to figure out what is my x and what is my y. So my x is my independent, my y is my dependent, or the thing that is being predicted. Okay. We want to find out how much water in ounces a person will consume if the temperature outside is 95 degrees Fahrenheit. So what I'm trying to predict is water consumption. Okay, so water consumption is my y variable. What am I using to predict water consumption? Well, the temperature outside. So temperature. Okay, so that means that my x right here is talking about temperature. This y right here is talking about water consumption. They gave me an x variable, or a temperature, of 95 degrees Fahrenheit. So my x is 95. Therefore, to find water consumption, I should need to plug this x value into this equation. So negative 96.9 plus 1.5 times 95. Or that will give me 45.6. And since y is talking about water consumption is measured in ounces. This would be 45.6 ounces. And that's the only thing they were looking for there. Okay. Now, understanding this equation and putting it back into English, or understanding the slope. Okay, so the slope of the line in this case is b because it's y hat is equal to a plus bx. Remember the number right in front of your x, that's your slope. So the slope of the line b describes how changes in variables are related. Okay, so how are we going to put this equation back into English? Well, this is the interpretation. The slope of the best fit line tells us how the dependent variable y changes for every 1 unit increase in the independent x variable on average. Okay? So if we look at this right here. So this is the equation that we just predicted, water consumption and temperature. We're going to put this back into English. So we say for a 1 blank increase, because it said the slope of the best fit line tells us how the dependent variable y changes for every 1 unit increase. Okay, what's increasing? Well, it's in the independent variable. Okay, so for a 1 unit increase in the independent variable, this is going to tell us how the dependent variable will change on average. Okay, so in this right here, we said that x was temperature and y was water consumption. Okay, so our independent variable is x and our dependent variable is y. So for a 1 unit increase in the independent, or for a 1 degree increase in the temperature, the amount of the dependent or water consumption will go up or down. Now, come back here, let's read it again. The slope of the best fit line tells us how the dependent variable changes. Okay, so I need to look at the slope right here. So my slope is a positive 1.5. So that means my dependent variable will go up because of this positive right here. If that was a negative, it would have gone down. But since it's positive, it's going to go up. By how much? Well, how much is the slope? And it's 1.5 ounces. And it's not going to go up 1.5 ounces exactly. It's going to go on average. Because remember, this whole thing right here is an estimate. Okay, so we can't pinpoint how much our dependent will go up or down. It's going to be on average because this right here is an estimate. Okay. Note, we'll use the word up since the sign right before the slope is positive. If it was negative, we would have used the word down. Okay, and that's the final thing right there. For a 1 degree increase in the temperature, the amount of water consumption, which should be right here, would go up by 1.5 ounces on average. And that's it. Now know everything I know about stats. There are no other videos that you should watch after this point. You've completed all of them. Good job.